In this lesson, we are going to look at expected value to determine if a carnival game is considered fair. So in a game of chance, a game is considered fair when the expected value is equal to 0. Remember, your expected value is what would happen in the long run. Expected value of a discrete random variable is equal to the mean. And how do we calculate that? Well, we find the sum, meaning add it all together, of each random variable times the probability of that random variable occurring. So let's look at a specific example. You throw a die. If you win $2 when the number is even and you lose $1 when the number is odd, what is the expected value? If you paid $1 to play the game, will you win in the long run? So I'm going to say that X is the amount I win. Okay? And I'm going to make my probability model. So I'm going to have two rows here, X and the probability of it occurring. So what happens? Well, I win $2, but if I paid $1 to play the game, I've really only won $1. And if I lose $1, well, that would be -1. And the chance would be 50 cents or 50% on each because they're half the die is even and half the die is odd. So to find this expected value, I would take the row times the this value times this value, each X times the probability of it occurring. This computes to 0. So this would be considered a fair game because in the long run, the average amount I can expect to win is 0. So what I pay out will equal what I bring in. It says in a casino, a game costs $3.50 to play. You draw one card from a deck. If it is a heart, you win $10. If it's a queen of hearts, you win $50. Is this game fair? So we're going to be making a probability model. I'm going to kind of do this one in two columns. So I'm going to say X is, again, the amount I win. So what do I win? Well, I can win $10, or I can win $50, which would be awesome. Or I guess I don't win at all. I would win 0. But sometimes as I think about this, I make a separate row where I think about like the net gain, where I think about after I paid. So if I paid $3.50 to play, that really means that my net gain would be $6.50. And if I paid $50, then that would be $46.50 because $3.50 is what I paid. And here, if I don't win anything, I've lost $3.50. So I'm -$3.50. Now the probability, I'm going to start with the queen of hearts. There's one queen of hearts, so 1 out of 52. If I win any other heart, well, there's a total of 13 hearts, so that would make 12 out of 52. Here, I could reduce that, but I'm just going to leave it. And then the rest of the deck, everything that's not a heart, would be the other 3 suits, so 3/4 of the deck, because these two would be 1/4. Okay? So my expected value, okay, would be the probability times, I'm going to do times the net gain, like what after I've paid out, is this fair? So I'm going to do the probability 12 out of 52 times $6.50, what my earnings would be after I include what I paid, plus 1 out of 52 times $46.50 plus 3/4 times -$3.50. Okay, and what would I expect after I have paid out and played? I get a value of approximately -0.23. So in terms of expected value, this is money. So this expected value tells me if I play many, many times, I can expect to lose 23 cents per game, so the game is not fair. At Spring Fling, the math department designs a dice game. Learners must roll 2 dice and record the sum. If you roll a 2, 3, 4, 10, 11, or 12, you win $5, and then the sums you see in the screen will cause you to lose $3. Find the expected value for learners per game. So I'm going to say that my random variable is the amount of money a student wins, or a learner wins. And I'm going to create a probability model to show that. So potentially, let's see, a learner could win $5, or they could be in the hole $3. And I have to think about what's the chance of each of these things occurring. And in order to do that, I think I need to look at my sample space. So if I roll a die, I could get 1 through 6, but I need to consider that I'm rolling 2 dice and finding their sums. So I'm going to sum 1 and 1 to get 2, then I sum 2 and 1 to get 3, and I continue this, adding the 2 dice together. Next route, 2 and 1 is 3, 2 and 2 is 4, 5, 6, 7, 8, 3 and 1, 4, 5, 6, 7, 8, 9, 4 and 1 is 5, 6, 7, 8, 9, 10, 5 and 1 would be 6, 7, 8, 9, 10, and 11. If I roll a 6 and a 1, that's 7, 8, 9, 10, 11, and the highest sum I could get is a 12. So the probability then of winning $5 occurs when I roll any of these values. So 2, 3, 4, 10, 11, or 12. So let me change that to highlighting 2, 3, 4, 10, 11, or 12. The ones highlighted in green are 6 out of 36 I stated that wrong. Excuse me, that would be 12 rather, out of 36, which reduces to a third. Everything else would be 2/3 because my probability has to sum to 1. So then my expected value is equal to the mean, which is 1/3 times $5 plus 2/3 times negative $3. That gives me an expected value of negative 33 cents. This means if a learner plays many, many times, he can expect to lose an average of 33 cents per game. In the final example, a player rolls a die and receives the number of dollars equal to the number on the die, except when the die shows a 6. If a 6 is rolled, the player loses $6. If the game is to be fair, what should be the cost to play? So again, to understand this, I'm going to build my probability model. I'm going to define my random variable x as the amount you win. So you could potentially win $1, $2, 3, 4, 5, or you could lose $6. The chance of this occurring, well, on each die, there are 6 sides, so each outcome could occur 1 out of 6 times. So to figure out if the game is to be fair, what should be the cost to play, we need to determine the expected value. So when I take 1/6 times each outcome, I get a value of 1.5. I'm going to make this money. This means on average I would be winning $1.50 every time I play the game. So to make it fair, I would need to pay $1.50 for every game for it to balance out to 0.